Right, so in this installment of the series, we're going to look at a couple common machine learning algorithms that will then apply in some of the examples. Again, there's lots of options. Here I'm mainly picking some of the most common methods that we use in GIS and remote sensing specifically. Okay, so why machine learning as opposed to some other methods such as linear regression or some type of parametric method? Okay, so the first good reason is that these methods are non-parametric, which means that they don't generally have distribution assumptions. So that means they're generally better at working with complex feature spaces, complex nonlinear relationships, or noisy data. It's generally been shown in a wide variety of use cases that machine learning methods tend to outperform traditional methods such as like linear regression or logistic regression for the same classification problem in terms of or regression problem in terms of the assessment metrics. So they tend to be really robust and make strong predictions in comparison to some of the other methods. Some of the trade-offs is a lot of these algorithms can make strong predictions, but they're actually fairly complicated models, so they're a bit of a black box. So if you're worried about interpretability, that can be a bit of an issue. It can also be noted that more recently, deep learning methods have been developed and are in some cases outperforming machine learning. However, they tend to need a lot of data. For image processing, we're generally using things like convolution stuff, which isn't always applicable for different use cases. So we're not, again, discussing deep learning in this class, but I did just want to note that it is sometimes it's a new field, it's advancing, so it's building on top of machine learning, and it's going to probably be a better option in some cases than machine learning, but not in all cases. Okay, if you're wanting a good, just general reference book on machine learning methods, I recommend this text by James and others. So, An Introduction to Statistical Learning. You can buy this book if you want. If you just like to, read it and don't want to buy or have a hard copy, you can download a free PDF version, like legally, right? So they provide that for free. Fairly recently, they came out with a new edition that includes some additional content, like on deep learning, for example. So this is kind of people's general go-to book on machine learning and statistical learning methods. It starts off with things like simple linear regression and generalized linear models and logistic regression and generalized additive models, and then talks about tree-based methods, ensemble trees, support vector machines, k-nearest neighbor, so on and so forth, and even some like clustering or unsupervised classification methods. I think it does a good job of balancing like the concepts and the math and the practicality of doing this type of work. So I highly recommend that if you're going to do any deep learning that you have a look at this text. Okay, so we're going to start off with arguably one of the simpler machine learning methods, and this is the k-nearest neighbor or KNN algorithm. So basically the idea here is that you are comparing a new sample to other features within a feature space. So in this image, I basically have a two-dimensional feature space. So let's say this is like the red band, and this is the near-infrared band. So you could plot every data point within that feature space as a XY coordinate pair. So its red band value is X, its near-infrared value is Y, right? And effectively, you are going to then try to take your new sample and relate it to the samples within that space. Okay, so in this example, all the dot color represents categories. So you basically have a yellow class, a blue class, and a green class. The red dot in the center is the new sample that we want to try to predict or classify. So in this feature space, and again, this is just two-dimensional, the idea is that you're going to look at the features that are nearest to it or have the most similar predictor variable values, right? So, for example, if we look at the nearest within this like kind of orange ring, we have 1, 2, 3, 4, 5, 6, 7. So looking at the 7 nearest neighbors, 4 of those are blue, 2 are yellow, and 1 is green. So that means that the majority of the neighbors close to this point are in the blue class, so we would assign this new point to the blue class. Now, if we look further out, so out to the edge of this green ring, then we have our 7, and then 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So if we're looking at all these neighbors now, the actual most dominant class is actually the yellow class now. So we have 1, 2, 3, 4, 5, 6 blue, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 yellow, and then 1 green. So now it would get classified to the yellow class. Okay, so this is fairly simple to visualize in a two-dimensional space, right? So the distance, there's different ways to measure distance, but it could just simply be the straight line distance in the feature space. So you could figure that out with like Pythagorean theorem, right? If we'd expand this to a three-dimensional space, then effectively that would be locations within the volume of like a cube. That's still fairly easy to conceptualize. When you get up to say like 4 dimensions, that really can't be conceptualized because we only have 3 spatial dimensions to work with. But that can be described mathematically. So we can determine the distance from a new sample to other sample locations or training data samples in a large number of dimensions. So the number dimension in this case is the k parameter. Okay, so how this works for a classification problem is generally we just use the majority class. So whichever class is the majority of all the k nearest neighbors. Sometimes you can apply things like distance weighting, where nearer features have a higher weight than features that are further away. For regression, generally instead of taking the classification, we're taking the continuous measurements of the dependent variable at the nearest samples and taking an average, or taking a distance-weighted average where near features have a higher weight in the average. And then for probability, we generally are using the proportion of classes of the neighbors as opposed to the count to get a probability. And again, you can also incorporate weight so that near features have a higher weight in the probability than the output. So in short, or than ones that are further away. So in short, k-nearest neighbor can be used for classification, both binary and multiple class, probability, which is effectively just the type of classification, and also regression is just a little bit different in terms of how it's implemented. So this is actually conceptually pretty simple. The idea is find all the nearest features in the multidimensional feature space, and then use those near features to determine either the class probabilities, or value for a continuous variable for your new sample. Note that there are different measures of distance. So generally we talk, for simplicity, we talk about Euclidean distance, which is just simply like the straight line distance. So again, in two-dimensional space, it'd be like the square root of x squared plus y squared, right, to get the straight line distance. But there are other estimates of distance. So for example, the Hamming distance is sometimes used for when you have categorical predictor variables as opposed to continuous. There's this Minkowski distance, which you see here. We have this this p term, so you can not just use like the square, you can use a different term there. And then the Manhattan distance, summing up lengths in multiple directions as opposed to like a straight line distance. So anyway, what we mean by distance can be defined mathematically differently depending on different contexts. One thing you should note is that if you're worried about calculating distances, then that means that if the predictor variables use a different scale, then that's going to kind of be a problem. So if predictor variable A is scaled from 0 to 100 and predictor variable B is scaled from 0 to 1, then that means that predictor variable I guess the second predictor variable B, it's just going to seem like those points are actually really close in comparison to the A values, but it's just actually different in measurement scale. So generally it's best to actually have all your training data, well, it's not the best, it's required that all your training data be on the same scale or rescaled. And luckily caret can do that for us with pre-processing steps, so we don't have to worry about doing that manually. But it is important that all your values use the same scale. Okay, so whenever a person is using k, nearest neighbor, they have to decide what value to use for k. So k, again, is the number of neighbors that you're looking at. Generally, small values of k means you're going to have more impact of local noise, whereas large values of k might actually generalize or smooth the data too much. So generally, we look at like 3 to 10, but it really depends on the problem. What we'll look at later is that we tend to actually try to determine the best k value using tuning operations, like k-fold cross-validation with like a tuning grid. So in short, you don't generally know like a priori what the best value of k or the number of neighbors to look at is going to be. So that needs to be tuned or optimized. Again, we'll talk about those techniques later. As a kind of a specific case, if you're trying to predict two categories, it's generally a good idea to use an odd number of layers because that means you can't have a tie, right? So for example, if you use 10 nearest neighbors, if you could have 5 and 5 and then there's a tie, right? If you use 11, then there can't be a tie. Now if you're predicting multiple classes, then there's too many options at that point or outcomes, and having an odd number is not going to guarantee that you're going to not have a tie, right? So that only really applies in a two-class situation. Okay, so some of the strengths of k-nearest neighbor is that it's non-parametric, so it doesn't have distribution assumptions. It's conceptually pretty simple, and it's not really stochastic. You give it the same training data, it's always going to make the same predictions because it's just based on distance from distance within the feature space. Some weaknesses is that it can be slow. That's because every time it makes a prediction, it's having to compare that new sample to all the samples in the feature space, which can be kind of computationally intensive. And that's especially true if you have a large training set because there's more input features or more features to determine the neighbors from, right? It tends to be negatively impacted by noisy or irrelevant features. So if you give it a lot of predictor variables and some of them are useless or noisy or irrelevant, that tends to negatively impact the accuracy of the assessment. And basically that's because it's trying to solve a problem in a larger space where a lot of those dimensions are just useless or confusing or like confounding. Again, you need consistent scale across variables so that they're all treated equally in the distance calculations. And then generally, this is a fairly simple technique. I generally find that this is not the optimal technique. Other methods tend to outperform it. Okay, so moving on to our next method, and that is we're gonna look at decision trees or DTs. So sometimes these are called classification and regression trees or CART, decision trees, DT, classification trees, CT. I'm just going to use the term decision trees here. Regression trees are another option. Okay, so this is also conceptually pretty simple. The idea here is that we are taking the data and recursively partitioning it into more homogeneous subsets. So you can think about this as kind of like a dichotomous key, right? So in this example, basically the first split is based on slope. So if the slope is greater than 6.2, then it goes to yes. And if it's less than 6.2, then it goes no, right? And then the next break is based on the green band, and then the brightness, and then the slope position, right? So imagine like you have a key that you're trying to like identify like a leaf with, or like an insect, right? So if you're identifying a leaf, it might ask you some question about the venation pattern, right? And then once it asks you about the venation pattern, it might ask you about like the width to length ratio or the texture of the leaf or something, right? So effectively you answer a bunch of yes/no questions, and eventually that works down to a prediction, right? So the difference here is that instead of basically a user or like a programmer basically coding in all of these rules, the algorithm is using the training data to come up with these rules or the best binary splits to recursively partition the data. So that's effectively the idea. So recursively partition the data into more homogeneous subsets. Again, specifically, it's binary recursive partitioning, so repeated yes/no partitions. It's going to be the best partition is going to be based on some measure of refinement. We'll talk about that in a few minutes. At the bottom of the tree, we have what are known as the leaf nodes. So those are the final predictions. So you can see here, these are your different categories. And also you can have the same category come out at different spots. So a different set of rules that define the same category, right? So here's shadow, for example, and here's shadow again. It's noted that whenever you let these trees grow with a large depth, so lots of partitions, that tends to result in overfitting, which means that it's overfitting or doing too good of a job of predicting the training samples and won't generalize well to new samples, which is really what you want. So in order to fix that issue, the trees need to be pruned, which generally means you're basically cutting off these lower branches or not letting it grow to like a very with a lot of depth. Okay. Okay, so here's basically like how this works. So again, we start with some data. We apply some type of rule, so binary rule. Then that splits the data into subsets. They're hopefully more homogeneous than the original full data set. Then those subsets have rules applied to those, which then break into more subsets, more rules, and eventually we get down to our leaf nodes. Again, you can have different pathways that yield the same prediction, right? So, for example, in this kind of conceptual example, the B class comes out at multiple locations. So again, recursively partitioning the data into more homogeneous subsets. Here's an example of why it is that we want to prune the data. So this is an example that was provided by Dr. Tim Warner. Okay, so again, if we don't prune, we basically let the trees grow with a lot of depth, and that tends to result in overfitting. And that's actually shown here in this demonstration. So this is the result on the test set. So before pruning and after pruning, and then the results, on the training set and then the test set. Okay, so before pruning, the tree size is 713. So there's 713 partitions or splits. And there's an error rate of 1.6% on the training set, but a much higher 17.6% on the test set. So when you have very high predictive accuracy on the training set, but a lower predictive accuracy on the test set, that tends to indicate overfitting. So it's doing a really good job on the training data because it's overfitting to it, but then it's not generalizing well to the new test data. Then after pruning, now we only have 231 divisions, so split rules within the tree. And you can see in this case, the error on the training set actually went up. So it did a worse job at predicting the training samples, but the trade-off was that it's now doing a little bit better job on the test data. So it's not overfitting as much to the training data, which means that it's doing a better job at predicting or generalizing to new samples. And again, that's really what we want. We want to have a tree where it does, or a model that does a good job at predicting or generalizing to new data points, because that's how it would be used. So this is an example of why we need to prune decision trees. In R, and specifically using the RPart package, which is implemented through, they can be implemented through caret, we use the CP parameter to control the level of pruning, and that's known as the complexity parameter, or CP parameter. So this is used to control the balance between model overfitting and model underfitting, or like overgeneralization, right? So again, the goal here is that we want a model that generalizes well and does not overfit to your training data. However, it shouldn't be so general that it's not really able to model like the complex patterns in the data set. So again, we don't really know ahead of time what the best CP or complexity parameter is going to be for a specific classification problem or model. So generally that means we need to test different CP parameters So this can be done using a tuning or optimization process. So CP, or complexity parameter, is another example of a hyperparameter. So larger CP values, or complexity parameters, are generally going to result in smaller trees, and smaller CPs are going to result in larger trees or less pruning. There are some other hyperparameters that can be defined or optimized for decision trees. One example is the maximum depth of the tree. So you can set a maximum number of splits. So that's effectively the maximum number of splits from the beginning to the highest number of splits, or set of binary decision rules. You can also set the minimum number of data points in a node that is required for the node to be split further. So basically, if you can set a minimum, and if there's, say, less than, say, I don't know, whatever your minimum is, like 10 data points in a split, then it's not going to try to split that subset again. So those are some other hyperparameters that a user can define on top of the CP parameter. So again, the idea here is that like a programmer that's like hard coding in these rules. Instead, the algorithm is going to learn these rules from the training data using the supervised learning process. So in order to do that, there needs to be some measure of model performance. So generally, we use a couple different options. There are a couple different options for this. So one option is entropy, and this is effectively a measure of how homogeneous a split is. So if all of the data points from one class end up on one side of the split, then that's going to result in an entropy of 0. If which would be a good split for that specific class. If the data points are evenly split between the two partitions by the split rule, then that's going to result in an entropy of 1, or a bad split. So effectively, it's a measure of how homogeneous a split is relative to a specific class. The higher proportion of the data points that end up on one side of a split versus the other, the better split rule that is deemed to be. Information gain is similar to entropy, but the idea here is that it looks at the decrease in entropy before and after a split, so comparing the change as opposed to just the absolute entropy. So calculate entropy before the split, calculate it after. The maximum decrease, a larger decrease, indicates a better split. And then another method is the Gini impurity index. So this is a measure of how often a random element from the set would be incorrectly labeled if it was randomly labeled according to the split rule. So the idea here is this is minimized when all cases from a specific class or category fall on one side of the boundary versus the other. So it's actually a similar concept to entropy. It's just a different way to represent that mathematically. So these are three options of how we can determine, or how the algorithm can determine, what optimal splits are within the feature space for the specific task. Note also that decision trees can be used for regression. So before we were kind of talking about the leaf nodes being categories, right? So class A, class B, class C. In the case of regression, instead of the end nodes or leaf nodes being a single category, they're going to map to a range of values. So a range of values for the variable that you're trying to predict, the continuous dependent variable. So, for example, this represents some data points. These are estimating CBI, which is the compound burn index or composite burn index. It's an index for forest fire severity using a band ratio derived from Landsat, so shortwave and near infrared. Or sorry, this is from Worldview 3. So the black dots represent the actual data points, and you can see a clear correlation here between the band ratio and the metric we're trying to predict. So here I fit a standard just linear model to the data, and the model here is represented as the predictions for each of the points as these red diamonds. So that would be a linear model prediction. In contrast to that, the blue like asterisk signs, those are the predictions using a decision tree. So here you can see this really clear like kind of stair-step pattern, right? And the reason why we're seeing that is because the decision tree is effectively predicting down to the leaf nodes, where each leaf node represents a prediction over a range of values. So these stair steps are basically a remnant of predicting those value ranges. If you're looking at this, it does look just, kind of qualitatively or visually that this decision tree is approximating this relationship a little bit better than the linear trend. There's a bit of a curve to this, so a straight linear trend is probably not optimal. Maybe some type of like polynomial would be better. But anyway, that's just kind of the goal here, is just showing you how you're predicting ranges of values in the case of regression, as opposed to categories in the case of classification. Okay, so some strengths of the decision tree method is that it is non-parametric, so it doesn't have distribution assumptions, deal with complex data. It's fairly easy to interpret these models, at least to a point. If you get really, really large trees, those are hard to completely understand. But, if you don't have a lot of splits or it's pruned back, sometimes you could step through the decision process and kind of understand how each individual data point was predicted or why it was predicted. So, yeah, so it's interpretable, but only to a point. It depends on how complex the tree is. There's not a lot of user-defined parameters or hyperparameters to tune. We have the CP parameter, also the max depth and the minimum number of samples. Those are generally not too difficult to tune, right? So it's pretty easy to implement kind of out of box. You can use it for regression and classification, and with classification you can also get probabilities. This is unlike k-nearest neighbor. This is not sensitive to scale. So you can have different variables be measured on different scales. You can even include categorical or nominal predictor variables. It doesn't really matter. So you don't have to like pre-process everything to be like the same scale. You can have both numeric and categorical or nominal predictor variables. It's generally quick to train and also to apply or predict back to new data, and it can work pretty well when you have large training data sets or have to predict back to a large sample. Some issues is that small changes in the training set can result in big changes in the tree structure. This is kind of a stochastic method, so if you run the same model over and over again, you actually can end up getting different trees and different output, or different tree structures, different splits, different rules, and that tends to be more variable when you have a smaller data set. It's not generally robust to noise in the data, or having a lot of predictor variables that aren't super useful. It suffers from the local minimum problem, which is also a problem for things like artificial neural networks, which like deep learning algorithms are built on top of. The idea here is that basically it can land on a suboptimal solution as opposed to the optimal solution based on kind of the loss or cost that you're modeling against. That's an issue for lots of algorithms, and a lot of work goes into trying to avoid that issue. So that's a big part of like how optimization algorithms work for deep learning, for example. And then the other issue is that you do generally need to prune to try to minimize overfitting. Okay, so the next couple examples are effectively just building on top of decision trees. So we're not going to talk about boosted decision trees in detail, but I did at least want to explain what they are kind of conceptually. So the next couple examples are ensemble decision tree methods. So the idea here is that instead of using one single decision tree and all of its associated rules and splits, you're actually going to use a bunch of decision trees that work collectively as an ensemble. So boosting is effectively one way to combine a lot of decision trees as a single model. So this is an iterative process. The idea is basically that you use the entire training data set to train a tree. You then look at the errors in the classification, and in the later trees, you try to prioritize predicting the samples that were misclassified in the prior trees. So the idea is that it's iteratively trying to improve the prediction as it generates new trees in the series. Turns out that this really isn't a single method. It's actually kind of a broad group of methods because there's different ways to implement a boosting process or to do this iterative misclassification repair process. So examples include add a boost and the C4.5, C5.0, gradient boosting. More recently, we have like extreme gradient boosting decision trees, which use like optimization algorithms similar to like deep learning algorithms use. And those tend to be slow, but they're actually providing some of the best performances that we're seeing for modern machine learning. So anyway, this is a pretty powerful technique. Because it's based on decision trees, it can do both classification and probabilistic prediction, again, just kind of a subcategory of classification, or regression for continuous variables. Because you're using a bunch of decision trees collectively, they don't actually have to be pruned like you do for a single decision tree to combat overfitting. And then generally in most cases, boosted decision trees or these ensemble decision trees is going to outperform just a single decision tree. So in summary, boosted decision trees are a variety of different methods where you're iteratively creating a series of trees and you're trying to fix prior misclassification results from the prior trees in subsequent trees. So it's, again, an iterative process. Again, we're not going to get into detail about that. I just wanted to mention it. Instead, what we're going to mainly focus on as an ensemble decision tree method is random forest, or RF. Random forest was introduced in 2001. This is the original paper here. It was published in Machine Learning and was originally created by Leo Bremen. So this is similar to boosted decision trees in that it's an ensemble decision trees, but how it makes the ensemble is a little bit different. Okay, so first off, for the measure of impurity or trying to determine what the best split is, it's generally going to use the Gini index of impurity as opposed to the entropy or information gain. So that's generally just how random forest is implemented. That's the decision algorithm of choice. Again, it's an ensemble decision tree method, so it's not just one tree, but it's a series of trees that are collectively working or acting together. In contrast to boosting, instead of using all the training samples in each tree, it's going to use a random subset of the training data in each tree, and also at each splitting node, it's only going to be allowed to select from a random subset of all the available predictor variables. So again, looking at the structure, basically in each tree, it's going to use a subset of the data, and also at each node in the splitting process, it's only going to be able to see a subset of the available predictor variables. So you might think, well, why is that better? I mean, if each tree is seeing less data and less information, isn't it going to be worse? And it actually turns out that that's actually true. So for a single tree, that's going to be a weaker predictor or a weaker classifier. But what you end up with is a large set of trees that have all seen slightly different sets of variables, slightly different sets of training data. So you have a set of weak classifiers that are not as heavily correlated with each other. So because there's a lack of correlation between the different trees in the model, this results in basically a better model generalization after the fact. So the idea here is that this is a strong ensemble of a set of weak classifiers. So because you have a set of trees as opposed to one tree, how do you actually get like a final categorical prediction at the end? Well, generally that is done based on majority voting. So if you have, say, 500 trees in your model and 450 of them think that this new sample is a forest class, then you're just going to predict to the forest class. And also using the kind of proportions of the votes, you can estimate class probabilities. And regression works similar to how it does for a single decision tree. Okay, so again, just some notes about random forest. Again, it uses the Gini index of impurity as opposed to entropy or information gain. So this is a measure of impurity of one class versus the other classes. So a better split is one where a large number or large proportion of the samples from a specific class end up on one side of a split. So high Gini index values indicate impurity or a bad splitting rule, and low values indicate a good splitting rule, or a more pure split. So a large proportion of the data ending up on one side of the split. Again, each tree doesn't use all the training data. It uses a subset of the training data to make the trees less correlated. And to do that, it specifically uses this process called bagging. And bagging is effectively just bootstrap sampling or random sampling with replacement. So the idea generally is that for each tree, 2/3 of the data by default is going to get fed through the tree, and 1/3 will be held out. So imagine you have a bag of marbles that represent all your training samples. So you shake up the bag, pull out 1/3 of them, use those for training. And then in the next tree, you would throw all those marbles back in, shake it back up, pull out 2/3, and then run those through another tree. So each tree is getting 2/3 of the data, but it's going to be a different random partition, right? Some of the samples will overlap, but they're unlikely to be exactly the same. So it's just effectively random sampling with replacement. For the hyperparameters for a decision tree, the most common parameters we worry about are the number of trees. So that's sometimes defined as in tree or trees, depending on what implementation you're using. And also the number of variables randomly selected for splitting at each node, which is generally the mtry parameter. So for the number of trees, it's generally been shown that if you use a large number of trees, say like 500 or 1,000 or 2,000, it doesn't actually cause overfitting. So we generally don't always or have to tune that parameter. We can always just use a fairly large number of trees. However, that the more trees you have, the longer it's going to take to train and then predict. So there is a bit of a trade-off there. You'll see in the hands-on modules where we work in R, there are ways to look at how many trees are required to kind of stabilize the prediction. So having a large number doesn't cause overfitting, but it can be computationally less efficient. Depending on the problem, the mtry parameter, or the number of variables that it can randomly select from for splitting at each node, can have an impact on the performance. The default is to use the square root of the number of predictor variables generally. However, you can test that. So generally, the options are basically 1 through the number of available predictor variables. Another variable that's not tuned as often but is available is the min, or the minimum number of data points in a node that is required for the node to not be split further. Again, that's just the same as for single decision trees. Okay, so here's some strengths for the random forest algorithm. So first off, it's non-parametric, so again, we can deal with complex, noisy data. It generally doesn't overfit bad. Some early claims said this algorithm did not overfit, but that's not really true. All machine learning algorithms overfit to some extent. It just doesn't tend to be a really large problem for random forests. You can use predictor variables that are measured on different scales, so they don't have to be standardized, like for K and N. They runs efficiently on large data sets. You can give it a large number of predictor variables, a large number of samples. For example, there have been studies that have used like thousands of predictor variables, and it's still been able to perform well. It's able to generate an unbiased assessment of its error. We'll talk about how that works in a minute. Again, because this is built on top of decision trees, it can do both regression, classification, and again, probabilistic predictions, which again is just classification. It can be pretty fast, both for training and especially for the final, for predicting the new data. There are tools built in to allow you to estimate the importance of predictor variables within the model. It's generally computationally lighter than boosting. Remember that boosting is iterative, so you make one tree, and then the subsequent trees are trying to repair misclassifications in the prior trees, right? By weighting those misclassified samples higher. So you actually have to do them kind of sequentially. Since all the trees in random forests are effectively just separate models and they don't affect each other, they can kind of be trained like parallel or separately, as opposed to, again, in sequence. So that makes it a bit faster. Similar to boosting, it doesn't require pruning, as is required for a single decision tree. There aren't a lot of user parameters, and it tends to not be that sensitive to its user parameters, especially the number of trees. but we do sometimes optimize the mtry parameter. And also you can use categorical predictor variables, not just continuous predictor variables. Some issues, it is supervised and it needs both training, presence and absence data, so yes and no, like in the case of binary classification. It's computationally intensive, but all these methods are. It's not fully automated. It's been described as a bit of a gray box, so it's somewhat interpretable because of some of these ancillary outputs that are provided, but it's still, it's still hard to really understand or comprehend what all these decision rules sum up to when you have all these different trees in the ensemble and all these different data splits. So it's not fully interpretable. Okay, so one kind of use of random forest outside of just making predictive models is to assess the importance of variables for making a prediction, or the importance of a variable within a model. So one complexity with this idea of variable importance is it's not always clear exactly what that means. There's not really like a nice, clear, hard definition of what variable importance is exactly. So it's a bit of a complicated concept. Using the random forest package in R, you can look at the variable importance assessments just using the importance function, which is called on the trained model. The way that this importance is estimated is that it randomly permutates one of the variables in the model, the variable of interest, and then it sees how much the model accuracy decreases. The more the accuracy decreases, the more likely that variable, the more important that variable is likely to be in the model. So here's basically the idea. So let's say you have 10 variables and you're trying to assess the importance of each variable. So for variable 1, you would randomly permutate the values. So what that means is you're effectively shuffling them so the values of the variable are not mapped to the correct data point, right? So all the other variables in the model in the trees are maintained while that other variable is basically broke, right? So you're trying to break the correlation or relationship between the predictor and the dependent variable. So you basically run the model through the tree, and if you see more decrease in performance, that indicates that that variable was important. And if you don't see much decrease in performance, then that would indicate that it's not that important. There's a couple different ways to estimate this. One is based on the Gini index, and the other is based on held out data. Mainly I use the out of bag error option, so that's mainly what we're going to talk about here. Okay, so just a couple other notes on variable importance. So again, the concept of importance is not necessarily well defined. There are kind of two extreme cases. So marginal importance is effectively just looking at the correlation or the importance of predicting the dependent variable with the independent variable of interest. So it doesn't take into account correlation between the variables or the other features in the feature space, right? So it's just how predictive the predictor variable A is for the dependent variable. In contrast, the partial or conditional importance, that's really more a measure of how important the variable is within the current feature space. So, for example, if variables are correlated with each other and you remove one of the variables, then some of that information is still there in one of the variables that it's correlated with. So in that specific situation, it would actually maybe appear to be less important because it's not providing a lot of additional information on top of what's available in the other predictor variables. So if your predictor variables are not correlated with each other at all, there's zero correlation, then the marginal and partial, or sometimes partial is called conditional importance, are the same, but when you have variable correlation, they'll be different. So you might say, well, then what do you want? Well, a lot of it's going to depend on what it is that you want, what you're interested in. So if you're interested in how important a predictor variable is in a specific feature space, then partial or conditional importance is probably more interesting. But if you really just want to have an understanding of how correlated or how predictive a variable is for the thing that you're predicting, regardless of the other variables, that's more of a marginal effect. So for example, if you were trying to determine what like a measure of whether like a drug is effective, then you maybe would just be interested in the correlation between the measure and the effectiveness regardless of other things. If you were trying to, so that would be more marginal. If you were interested in the correlation between, say, that like the added value of this test with existing tests, then you'd want to consider the importance in the context of the information added on top of the other tests. So that would be more partial. It should be noted that there have been some issues with kind of the typical permutation-based method for assessing variable importance with random forest. This can be misleading when the variables are highly correlated with each other, the predictor variables, if the variables are measured on different scales, if you have a mix of continuous and categorical or nominal predictors, and if your categorical or nominal predictors have different numbers of levels. So, for example, if there are more levels, categorical variables with more levels tend to have an overestimate of their importance in comparison to ones with a smaller set of levels. Strobel and her co-authors have done a series of studies on this that are really useful, and they're all linked here. Okay, so there's different ways then to kind of improve upon variable importance estimation using random forest. I like the method that's implemented in the party and the perm imp packages in R, which were generated by Strobel and her colleagues. So basically, this method uses a different type of random forest implementation that's based on top of conditional inference trees. And running the importance estimates, you can set conditionals equal to true or conditionals equal to false. When you set it equal to true, it attempts to try to estimate a more partial or conditional measure of importance. If it's set to false, then it's trying to estimate a more marginal measure of importance. Again, if the variables are not correlated, that's effectively the same thing. If they are correlated, these measures are generally going to be different. Note that because of the complexity of the tree structures, it's kind of difficult to tease out the correlation between all the variables. So this isn't going to give you like a purely partial or purely marginal estimate of importance. The idea is to take the original permutation-based importance and try to get a better estimate of marginal versus partial importance. I like how this works conceptually and how it's really well defined. It's pretty easy to use. So this is kind of my preferred method for actually assessing variables with random forest, as opposed to the kind of de facto or original method. This is just an example of how we use that conditional importance for estimating the importance of variables for estimating slope values, for example. This is from this study. It should be noted that there are other ways to assess variable importance or select a subset of variables, which we'll talk about later. So another option is this Baruda method, which is implemented in the Baruda package in R. We're not going to talk about that in detail. I just wanted to mention that it is another option. It can basically take a set of variables and categorize them as important, not important, or like uncertain or maybe important. And it's based on like comparison to like shadow or permutated variables. Okay, another kind of benefit of random forest is that because each tree only uses a subset of the training data, then you can actually get like an estimate of model performance using the withheld data in each tree. And that withheld data is known as the out-of-bag or OOB data, so out-of-bag data. So this has generally been shown to be an unbiased assessment of model performance as long as the training data are unbiased and randomized. If the training data are not unbiased and randomized, then that bias is going to exist within the out-of-bag samples, and thus is not really going to represent error when generalized to the entire population. So if you collected your training data in a randomized, unbiased way, the training data are representative of the population, then this out-of-bag error can generally be used as to enhance or in some cases even replacement for doing a traditional accuracy assessment using a withheld validation or test data. Again, as long as it's that assumption of randomized, unbiased data is met. Okay, so if you train a model with the random forest package, for example, and you simply call the model, it will give you back the out-of-bag error assessment. It's like an error matrix with error rate. Again, RF is capable of doing both probabilistic prediction and classification and even regression. Note that when you use random forest and your goal is to get back class probabilities, when you run prediction, you need to set the type to prob as opposed to the default, which is the class mode. So this can be used for both yes, no, so binary, or for multi-class probabilities. Okay, so the last example we're going to look at is the Support Vector Machine Classifier, SVM classifier. Okay, so this came out of like computer science in the 90s. It's a little bit different from some of the other methods that we talked about, like the tree-based methods. But it has been shown to be really powerful, and alongside random forest, it's generally kind of the de facto like classification method that we use in remote sensing now, and in the geospatial sciences. So the idea here, conceptually, is that you want to try to come up with the optimal boundary to differentiate classes. And the optimal boundary is going to be defined as a boundary that has the maximum margin between the two classes. So this, for example, is being defined here as the maximum or best boundary because it's the best gap or separation between the two categories. So it's not too close to one category or the other. It's kind of floating in the middle there. It turns out, so this separator in two-dimensional space, imagine this is like two image bands. In this case, it's going to be a line. If you try to expand this decision boundary into multiple spaces, instead of calling it a line, we generally call it a hyperplane. So, for example, in three-dimensional space, this line is now going to actually be a two-dimensional plane or separation. If we move into four-dimensional space, we can't really visualize that, but it can be described mathematically. Effectively, the dimensions of the hyperplane is going to be 1 minus the number of dimensions of the feature space. So 3 dimensions, you get a 2-dimensional hyperplane. 2 dimensions, you get a 1-dimensional hyperplane, or a line. 4 dimensions would be 3-dimensional, right? One other kind of unique component of the support vector machine method is that it actually doesn't use all the training data to specify or define a decision boundary. Instead, it's only going to use the points or features that are closest to the boundary in the space. And those are known as the support vectors, and that's why this is called support vector machines. Originally, this was developed specifically for to separate two classes, so Class A and Class B, for example. But it's been expanded for multi-class classification. The idea is to do like one versus all the others, or do them like in a pairwise way. So it's kind of like combining multiple models to do a multi-class classification. Obviously, in real space, you're going to have situations where you can't create a plane that separates two data sets completely. So you're going to have some samples that fall on the wrong side of the decision boundary. And in order to deal with that, there's a hyperparameter that can be set known as the cost parameter or C parameter or positive slack variable. And this basically this variable controls how much a model is penalized for having data points on the wrong side of the decision boundary. So it can be used to kind of balance between models that are overfit or models that are too generalized. Okay, another issue with this type of technique is that lots of boundaries between two categories are not going to be linear in the feature space, right? So you can't define a line or a hyperplane or in like a three-dimensional space that would separate the data adequately. So in order to expand the use of support vector machines in situations where the data are not linearly separable, researchers and developers have integrated this concept known as the kernel trick. So the idea is that you effectively take the feature space, so the multidimensional space that defines your features, your predictor variables, and you transform that into a higher dimensional space. And effectively in this higher dimensional space, you can have a boundary that now is much more linear. So you can effectively come up with a hyperplane that is a nice linear separation in this higher dimensional space when it actually would be nonlinear in the original feature space. And this is kind of explains that conceptually. So here we have this complicated boundary, and this is applying the kernel. And now in this new space, this complex boundary can be approximated as a linear boundary in this, again, higher dimensional space. Same thing here, we have a two-dimensional space, and then we have this complicated boundary. Expanding that into this kind of three-dimensional space, we can now approximate that as this nice hyperplane, right? So anyway, that's the kernel trick, and that makes it possible to apply SVM more accurately to data that are not linearly separable. This is an example from a paper by Mahesh Pal and Giles Foodie that shows, I think, pretty well what we mean by support vectors, right? So here we have three categories of different like agricultural categories. So wheat, this group here, sugar beet, this group, and then oil rapeseed here, which is the triangles. So the points that are shaded in are the support vectors. So basically what that means is that it's really only these data points that are shaded in that are being used to define the decision boundary to separate the classes. The rest of the samples are not. So it's really the marginal points that are used to make the decision, which is interesting. So that's that's different from a lot of the other techniques that we use in machine learning. Okay, so what about hyperparameters for SVM? What hyperparameters are required for this model? Okay, so first you can choose a different kernel to transform the data into a higher dimensional space. So there's options that include linear, polynomial, radial basis function, or sigmoid. I generally use the radial basis function for classification problems, or the RBF kernel. If not, then polynomial is probably the other common option. The other is the cost parameter, or the C parameter, and again, that has to do with how much the algorithm is penalized for having data points on the wrong side of the decision boundary. For kernel specific, for radial basis versus polynomial, there are different parameters for different kernels. So for example, the RBF kernel has this gamma parameter for classification. It has an epsilon parameter for regression. Polynomial has the polynomial order as a hyperparameter. So one complexity with SVM is there are multiple hyperparameters, and they're not always easy to tune. Again, SVM can be used for regression. The idea is that we're effectively performing a regression in a higher dimensional feature space as opposed to creating a classification decision boundary. But it's still effectively relying on support vectors. Okay, so some strengths of support vector machines. So can deal with complex nonlinear data, especially when the kernel trick is applied. It can be used for classification, regression, and probabilistic modeling. It doesn't have a local minima problem, as is with decision trees or like artificial neural networks. It actually only uses a small proportion of the training data to actually define the model, so it can be fairly fast prediction time. It generally isn't heavily impacted by outlier points. It's a fairly robust algorithm. It's generally accurate compared to some other methods. Whether or not you need to tune the hyperparameters is really going to depend on the problem. So sometimes you may see significant improvement with hyperparameter tuning, other times you won't. Generally, you're going to want to tune them. Again, we'll talk about that later. Again, some weaknesses. It's similar to random forest. You got to give it presence and absence data. It can't just work with presence data only. And the user-defined parameters or the hyperparameters may impact the accuracy, which means there's some cost in terms of computational time for tuning the algorithm. Okay, so that's the end of this section. In the next section, we're going to look at methods we use to assess model performance.